welcome to class. So today, if you haven't yet, remember to do the homework. So that's due by tonight. There's voltage dividers, current dividers, whetstone bridges, and superposition questions on there. Tomorrow will be your quiz, so it will be voltage and current dividers. So make sure you really understand that content. If you want practice problems, you can use the Eulaby chapter book questions, or you can use the Unit 1 practice problems. So they also are linked now to all of your homework type of questions. So if you reiterate those, you will have new problems that will come up. All right, any questions about going forward as far as what's due? Yes?
Is it possible for you to post the homework a little bit next week?
I will try and get it done actually tomorrow, so it will be a full week that you will have it due. And I apologize, I'm still trying to catch up. I thought I would be there, but I like to kind of do this so you guys have lots of extra practice, so it just takes me longer to implement them. So yes, I will take that into consideration, and yes, gladly try and get that earlier. So apologize again for this week. It did get delayed. So tomorrow they should be posted. Also, the quiz will be posted, but then next week's homework will be posted. Next week's homework will be the max power transfer, which we're also going to go over today, and Thevenin and Norton equivalents. All right, any other questions, comments? Oh, and the assignment as far as your weekly discussion is also due by tonight. So tonight is weekly discussion and homework. Tomorrow is quiz. All right, any other questions? Okay, so last time we talked about superposition, and then we started talking about the Thevenin. We'll go back and review the Thevenin quickly, and then I'm going to introduce you to the Norton equivalents, which is another type of equivalent circuit, and then we're going to talk about the max power transfer. So for the Thevenin equivalent, anybody want to take an attempt at describing why we want to do a Thevenin equivalent? What's the purpose of it?
Is it to simplify the circuit down so it's a little bit easier to solve for other factors?
That's it. So let's make a complicated circuit into these two simple elements, a resistor and a voltage source. And then if we put a load on this, then we can know how much current's going into it very easily and how much power would be then drawn into the device that's connected. Okay? So the Norton is the same. It's going to be a different form for an equivalent circuit, but the idea is the same. Make a complicated circuit into something simpler. So with that, we need to find two elements from the circuit itself: voltage, VTH, and resistance, RTH. So these were the steps of finding that we went over last time, and we went through an example. Paste. So we have an alternate form. So this is the Thevenin with a voltage source and a resistance, and this one is called the Norton equivalent. And the Norton has just a current source and a resistance to it also. So a couple ways you can do this. You can find the current source value right away, and then Rn is going to be RTH. Or you can use the transformation from finding the voltage first and then transform it into the current. So what would make these equivalent to each other? So with no load, what makes these equivalent? So what is the voltage? If I measure the voltage between here and here, what is that voltage? Correct, it's just VTH, right? Because it's an open circuit, so open circuit, there's no current flow. If I was to measure between here, what would I measure? So V here would be what?
IN times RN.
Correct. IN times RN. So to make these equal, let's put VTH, then VTH has to equal IN RN. And IN then would have to be VTH over RN. Or if you're transforming the other way, just VTH is IN times RN. So if you find one, you can transform to the other form. So what about RN and RTH? So to find RTH, you would short VTH, and then RTH is still the equivalent between A and B here. This is A and B. And if you find the equivalent on the A to B, IN is just an open, so your measurement is going to be RN. They're just going to be the same, right? RTH would equal RN. So you're going to find RTH or RN the same way. The difference is that, copy this. If I want to directly find the Norton equivalent, one way I can do that is to short this between A and B. And you'll see this in the book as SC, meaning short circuit, where I put an actual wire between A and B, and then I solve the circuit to find the current coming out here, which will equal IN. So IN will equal the ISC. So this is one other way of finding the Norton equivalent, is to short that wire between A and B, and that wire current that will go through it after you solve the circuit ends up giving you the IN value. I don't prefer this method. I prefer the Thevenin. And the reason is that this doesn't always work. Sometimes when you get a short circuit, it gets to be very confusing. Because you'll have all these different wires and you have to find out all of the currents in each of those wires and add them up to one current in a wire. And that gets to be very complicated kind of at your stage of experience, and so I tend to not like the Norton equivalent as much. So if you get really familiar with the Thevenin, which is where I encourage you to get familiar with that one, just note that you can transform it into the Norton from that. All you have to do is say IN is equal to VTH over RN, and then RTH will be RN. So recommend doing Thevenin, and if you ever needed to find the Norton for some reason because you wanted the current flow instead of the voltage there, I've never come across a situation where I've used the Norton. So I'll tell you, I prefer Thevenin. Most of your examples and problems will be Thevenin, so just make sure you know how to do that. But we can do the same example we did last time. So if we were to convert this from a Norton to, or from the Thevenin to the Norton, what would these values be? So this is what we solved last time, got 15 volts for VTH and 30 ohms for RTH. If I was to convert this into the Norton, what would be my current value here? So find IN and RN. And then use the poll to put your answers in. So these are all the same answers and they are correct. So, good job. So IN here so what we said before is RN is just going to equal RTH, and in that case it's the 30. So we have RN equals RTH is 30 ohms. And then from this, again, we can do the relationship of VTH has to equal IN times RN. So IN is VTH over RN. So 15 over 30, which gives me 0.5 amps. So that is where both those come from. All right, questions on that? So if I have Thevenin, I can easily convert it to Norton. So what if I had my original circuit and I want to, and I don't know the Thevenin, and I'm like, okay, I actually want to solve it this time using Norton instead. So with this, I would then go back to the first step, which is what to find a equivalent circuit. So if you go back to the steps, the first step is to choose a polarity for the load or the orientation of VTH. Then you're going to remove the load and calculate the open circuit voltage. So the first steps are the same. You're going to choose a polarity. Okay, I'll just write this. So 1, choose polarity. And then remove load. So removing the load, I'm going to actually remove the load first and then choose my polarity. I like to have plus always on the top, so again I'm going to choose my plus on the top. And the difference between the Norton and the Thevenin is instead of finding VTH, now we want to find IN. So this one is going to put short between A and B. And that will give me the IN. So once I find the current in this branch and going around in that direction, that's going to be IN. So if I do this, I need to find IN, and then after IN is going to be removing the sources and open between A and B again if you don't already have it open there. And find the equivalent R equivalent, and that will be your RN. So it will be your pathway between A and B, where A will be here and B will be here. I'll move that up. Okay, so go ahead and try to solve this circuit. Now directly to find the Norton equivalent. And then you can put your answers. Okay. Okay. It's a little hard to see in the back. So this is 40 ohms in this one. One 20 and 20. So I'm missing the creative ones that you guys did last time, 500 milliamps. The other, how else could you write 30 ohms? So yes, they should be the same. It looks like majority of you saw that. So if I have a wire in parallel with a resistor, it's only shorting the resistor. So this was also on your quiz, which some of you missed this concept. So do understand that if I was to highlight, so in between the green, I still have two elements, 40 and 20. And if I have a source in between those two locations, I am going to have current flow in there because it's a closed circuit. If I had a current source, which was what your quiz was, that current is forced throughout the whole branch. So there's current flow in the resistor, and therefore you have power in that resistor. So in this case with voltage, I have 20 volts, which means how much voltage is, and which polarity. So I would label it this polarity. This is also going to have 20 volts, right? So if I have 20 volts, and then I have to go down 20 volts in order to make that equal to 0. So because there's voltage, there's also current going through this, plus to minus. And so that current will be my IN current. This will have 0 current in just if a branch only has resistances in it and no sources, it's only shorting that element. So the 120 has no current flow, but there is current flow where there's a source in the branch. So that seemed to be a concept that quite a few of you missed on the quiz. So do understand that it does short the branch, but there's still a source in there which is going to force current to flow. So in this case, it will be 20 divided by 40. For the 0.5 amps, which is the same. This one. And then for the resistance, you do it the same way we did before, which is you're going to again remove the sources, and in this case that becomes a wire because it's a voltage source. And my pathway from A to B I see that these have that they're in parallel, and so my pathway gives me those two in parallel, which is 1 over 40 plus 1 over 120. So 40 in parallel with 120, which equals 30 ohms. And so that will give me the same answer as what I got before. Okay, questions on Thevenin or Norton? You guys good? Ready to move on? Okay, so we're gonna move back to the robo-bees. So when the robo-bees are flying, it takes power to be able to make them fly. And so one common thing that we try and do is get a maximum power transfer from a circuit into a device such as this so that we have maximum power. And so we want to look at, oh, I forgot. So, you know, these antennas that you can kind of see on here, there's one there. There's different antennas, but each of these, you want to have the maximum power in order to be able to get the most information out of them. So, different types of antennas, which are kind of a cool area of electrical engineering, is actual physical configurations of these. As mechanical engineers, I thought you guys might find these interesting, that you actually get different responses from different mechanical configurations. So how do we maximize the power to the load? So in order to understand this, we first want to be able to say, well, what's our equation look like for the power to the load? So go ahead and calculate the power here. So if this is labeled as VL, try and figure out an equation for the power. So take a minute, try and derive the equation for power there. So power over the resistor RL is what you're trying to write it. So you're assuming that you know VTH, RTH, and RL there. So in other words, write a power expression, power VL in terms of VTH, RTH, and RL. So fuzzy.
With this, since we're trying to find the voltage here, we're going to move our level. So I actually, so the current in this branch is ECE over That makes sense.
So is this like correct for this, like, straw on here? Or the straw on Thank you.
Yeah, so that would be your voltage across the chart.
I guess now we know the voltage and the correct
Yeah, so you need to use the current. Yep. Yep.
Oh.
And you can find it.
And then same for oh, yeah, and then if you
Oh, they're in series.
Right, easier to read now. So with this, since we're finding the actual, we need to find the current in this branch. So the current is gonna be what? I think a lot of you got this correct. What is the current here?
It's just VTH over the sum of the resistors.
Correct. So we have our I in there, and then what is VL? VTH what?
Times the load resistor.
Uh-huh.
Sum.
Correct. So you could note that it's a voltage divider, so you could find it that way. Or you could use Ohm's law. VL using Ohm's law, we know is I times RL. And then you note that that VL equation is the same whether I take the voltage divider or that. So power is going to be I times VL. So this becomes VTH squared times RL over RTH plus RL squared. So some of you didn't include RL, so you note that the current though flowing through there has to include RL, so it's VTH over RTH plus RL. Okay, so now we know a power equation. How does this help us to find max power transfer? So this is a squared term. Copy. If I was to graph this, it actually looks like this. So this is a graph of RL. So as RL increases, it actually becomes this form. How do I find a maximum from this graph? Do you remember?
Take the derivative.
Okay. And do what?
Find where it's equal to 0.
Correct. So I want to find this location right here, right? So this derivative, set it equal to 0. So taking the derivative of this power equation with respect to RL, set it equal to 0. And that's going to give us this point, which is maximum on this graph. So this is how I want to find a maximum. So go ahead and take a second to mathematically find this. Put the equation over here. So you're going to take this with respect to RL. As far as the derivative, set it equal to 0, and then solve for RL in terms of these VTH and RTH. All right, so again, you're trying to find the maximum. So taking the derivative of this with respect to RL, set it equal to 0, and then manipulate that equation to get RL is equal to the variables VTH or RTH, and or RTH. So taking the derivative, you have to note that there is an RL on the top and then there's an RL on the bottom. So you have to use the chain rule. So you take the derivative of the first component and then leave the second one, and then take the derivative of the second one and leave the first one. So the derivative of RL is just going to be the number out in front. I can take the VTH squared and divide it over to the 0 side, which also still stays 0. Same thing here. And so I get RL. Derivative of that is just 1. So 1 times RTH plus RL raised to the minus 2. And then you take the derivative of the RTH plus RL to the minus 2. The minus 2 comes down. And then you take the derivative of the element that's inside the parentheses. So as I bring minus 2, I subtract off minus 1 again. So that becomes minus 3. And then RL is just, derivative of that is just 1 in front of it. So there's also a 1 multiplied there. So then I combine the first term, I turn into a common denominator of RTH plus RL cubed. So I can add those two together, and then I can take that RTH plus RL cubed and multiply it by the 0, which becomes still 0. So then I have RTH plus RL minus 2RL. So RTH minus RL, and so RL equals RTH. So this is the condition, simplifies down to very easy, right? I can now look at a circuit. I can take the equivalent resistance of it, which is quite easy if there's independent sources, and then just set that RL equal to the RTH. That's going to give me my max power transfer out of the circuit. So let's look at an example. So let's first go back and do the example of the Thevenin. So take the Thevenin of this first, and then we'll look at the max power transfer. So this might be a little hard to read. So this is my RL resistor here. It's 72 ohms. So I'm going to remember to take that out when I'm finding the Thevenin, and then I'm going to put that back in at the very end. So take that out, determine your polarity, find the voltage between A and B here. After you've taken that out. So note that this has two sources, so you might want to use superposition to find that voltage. So go ahead and try and find those. So let's find VTH first. So just looking at VTH to start with.
either gonna be like, well, I can drop that voltage from the 9 volt drop plus the drop across R1. Or it's the drop across the R3 and R2. So those are two different pathways. So with it open, there's only gonna be one current flow, so you can find the current and then that would turn yeah, or find all the voltages across each resistor. And then it should be 9 volts plus the drop in R. For 4 ohms.
Oh, yeah, it's like, how do you find like B, so, like B doesn't know, like, so just like, oh, okay.
So you have to label that's 0.8.
Oh, yeah, ground, oh,
Yeah, you're right.
I guess it makes sense.
$40, $20. So I don't know if this helps to see this visually for the first. If you're using superposition, eliminating the current source would give you this circuit here. And so VA for this one is going to be either the drop across the 9 volt and the VR1. I don't have anything labeled here, so if I don't have something labeled, I can arbitrarily label it with something. So I could just call this VR1, this VR2, and this VR3. Again, that's just kind of an arbitrary labeling. With that, I also don't have current defined here, so I can also label a current. I can keep it in the same direction as what I labeled for the polarity of that. So I just call this, I1. Then I notice that VA1 is a node voltage, and so that's either going to be, this is going to be plus to minus, so this would be a +9 minus VR1 would be equal to VA1, or a green plus VR1 plus VR2 is equal to VA. Or it's also equal to VR1 or VR2 plus VR3. I can also see like, well, there's one current, there's just resistances in one source, so this meets the voltage divider configuration. So I can also say, so from here I could say I is equal to 9 over the summation of all those, R2 plus R3. Or I note that it's a voltage divider, so 9 times R2 plus R3 over the summation of all of them. Wait, R1. And then plugging in those numbers gives me 8.1 volt. I think 8.1. 120 plus 240, so 360 divided by, yeah. So 8.1 volts for this one. So there's my answer for the first part of the superposition. For the second part, if I eliminate the voltage source, I'm trying to, again, if I am a little confused, I want to start by labeling ground, and then I can label across every resistor a voltage, and then define a current if there's not one. So if I label this I12, that's going to be the same current going through both of these, but then I hit a node, and so I then have a different current that's going to go through IR3. So my unknown is this node here of VA, call it VA2. And in order to find VA2, hopefully you can see that it's also equal to a minus. So VA1 or VA2 here, remember, is a plus at the location, and then it's kind of a comparison, got some drop to ground. So my pathway would be that VA2 is equal to a minus VR1. And VR1 using Ohm's law is going to be I times R1. So if I can find I, then I know this solution. So finding I, if I notice again that it is a current divider this time, I have that I12 is equal to a minus IS times R3 over the summation of all the resistors in the branches. And so 50 milli, R3 was 240 all over 400. R3 which gives 0.03 or 30 milli. So 30 milliamps, and so VA2 will be a minus VR1, which is I12 times R1, which, what was R1, 40? Is R1 40? Okay, just making sure. 40, and so we get a minus minus 30 milli times 40 for a plus 1.2. Yeah. So adding both of these together, we get 8.1 plus 1.2. So VA, which is this node, (8.1 plus 1.2). Just double check. Minus. Oh wait. Plus, yeah, this is a plus. It's going the same direction. No? Let's do, no, it is a minus. Minus. Plus 1. PR1 minus, okay. So I12 becomes a minus and then minus plus, okay, 1.2. So 9.3 volts for VTH. All right, for RTH, you're going to find the pathway between A and B. And remember, wherever you've put the A and B locations, they become extraordinary nodes. So this location is an extraordinary node here at A. And B is also an extraordinary node. So with that, hopefully you can see that you have 40 is in parallel to 120 plus 240. So the 120 plus 240 is 360. So you have 1 over 40 plus 1 over 360, which gives 36 ohms. So questions on this? A lot of 6.1 volts, so questions?
Why do you say that it's a negative IS when you're calculating IR2?
Yes, this would be a plus, thank you. So I12 will be a plus because it's going, yeah, it's going in. So IR3, the way I drew it, would be a negative, but I12 will go in and then it goes down, so it actually is a plus, sorry. So this is a plus. So this ends up being a minus 1.2 for, there we go, 8.1 minus 1.2. So 6.9 volts. Okay, others that got 6.1, questions like how you got 6.1? Yes.
Got 6.1 from failing to realize that not all the current will go through the 40 ohm resistor.
Ah,
And as mistake corrected now.
okay.
It makes sense.
Okay, good. All right, others that got 6.1? Okay, everybody's getting more 6.9 now, so it was the current divider was a little bit more confusing. Back to the current divider. So yeah, you gotta make sure that you have two branches there, so the current has to split between the two. Okay, so now let's say, any other questions though before I go on?
Yeah, could you go
Comments?
one more slide? To the voltage. Right, there you go. Just want to show you this right. Thank you.
All right, any other questions, comments? Okay, so say we want to use this circuit and we want to get max power transfer. So redrawing this, we have VTH, which we found was 6.9 volts, and 36 ohms for RTH. So this is our Thevenin equivalence for this circuit. So now we want to put on, say we want to put on a load, and we want to try and get maximum power transfer. And say we have control over that resistance of RL, what value would we want to try to get it close to in order to get the maximum power transfer out of this circuit?
36 ohms?
Yep. As close to 36 ohms as we can get will give us max power transfer. Okay, that's it for that one. All right, any questions? Okay, I just put them on the wrong slide, but. Okay, so practice. So you guys have all the content that's gonna be on the first exam. So reviewing KCL, KVL, Ohm's law, using those to solve for circuits with variables within the circuit. Voltage dividers, current dividers were techniques on if I see this configuration, I don't have to go through each of the steps again to derive those equations. Superposition was another technique to get to a similar solution. And then Whetstone Bridge is an application that we've looked at. And now max power transfer is also another concept that we've done. So those are all the topics that will be on the first exam. So lots of reviews, lots of problems.
When is the exam?
I don't remember. Let me look it up.